Now Steve's going to cover engine operations. You'll learn about the typical aircraft engine and how to keep it running smoothly. You'll also see how different propeller systems can affect your airplane's performance.
We're going to start by looking at the fuel we put in airplanes. Then we're going to talk about engine operations. We're going to take a look at all the levers in the cockpit we use to control the engine and the gauges. Then we're going to look at the two types of induction systems that deliver fuel to the engine, which are fuel injection and carburation. We're going to give them a good working over and talk about the advantages and disadvantages of each. Plus, all throughout this module, we'll talk about some general operating tips so you can keep your engine running smoothly. One thing you want to know about aircraft fuel is it's just about the same thing we use in automobiles, except there's one big consideration. When you run out of fuel in a car, you simply pull over to the side of the road, go to the gas station and get some fuel. But if you run out of fuel in an airplane, you're going to have to make a forced landing. There are three grades of fuel used in general aviation planes. We have 80, which is red. We have 100 low lead, which is blue. And 100, or it's been called 100-130, which is green. Notice how the number of letters increase in the words. This should be a helpful aid in remembering the order of fuel grades. During pre-flight, you always check this color to make sure you have the proper grade of fuel. Let's say you can't get the fuel you normally burn. It's an acceptable practice to go to the next higher grade, but never to the next lower. As you can see, the airplane's placarded for 100 or 100 low lead, which means we can always use one of these two fuels, but we would never go to 80. That could cause knocking or overheating, which is what happens when you use lower than specified fuel. I'd like to mention, too, that auto gas cannot be used in airplanes unless there's a supplemental type certificate allowing it. During fueling, the fuel truck should have a ground wire connected from the truck to your airplane and from the truck to the ground. After the aircraft's been fueled, it's wise to wait about 5 minutes or so any water that might have been delivered with your fuel or any water on the tank walls will settle to the bottom of the tank where we can drain it out. Water is heavier than fuel, and we're going to look at that in just a minute. Another point I want to make is you want to always make sure these fuel caps are on tight. They always point into the airstream, and if there was only left on partially, one could lift up, fall off, and I guarantee that the 40 or so gallons of fuel would come out of here within about 6 seconds in flight. There's two ways water gets into the fuel tanks. The fuel truck pumps you contaminated fuel, or condensation collects on the fuel tank walls when the tanks are left partially filled. What happens here is like an ice-cold drink outdoors in the summer. Warm, moist air contacts a cold surface, causing water droplets to appear. At night, the cold walls in the fuel tank cause water to condense on them. The water then drops to the bottom of the tank. Now let's see what pilots do to check for fuel contamination. I'm under the wing of our piper here, and this is called a quick drain, and I'm going to fill my sample cup. Let's see what we've got. Notice the water in the fuel here, and we can see how the fuel is sitting on top of this clear water. We'd want to keep draining until we got all the water out. A couple feet from the quick drain under the wing, we'll find a fuel vent, and the reason the tanks are vented is to allow for an equalization of pressure when we're in flight so we can get good fuel distribution. On a hot day, if the tanks are filled, you'll also notice a little fuel drop out of here, which allows for expansion in the tanks. Next, we check the gascolator. We open it up, let fuel drip out for 3 or 4 seconds. Make sure we don't see any contaminants or water. Then we come and we close the gascolator. You'll find this at different spots on different planes. Sometimes it's accessible from inside of the engine compartment. Sometimes it's accessible from the outside, like this, you'll see on this piper. If there's any water in the fuel, it'll look like this on the ground. You'd want to just keep draining until you get rid of it all. Now let's look at some of the instruments and controls we use inside of the cockpit to deliver fuel to the engine. First, let's take a look at the fuel selector switch. The fuel selector switch lets you choose between tanks. As you can see right now, we're on the right tank. All we do is move it to the left tank, which allows us to feed fuel from the left tank to the engine. You want to make sure that when you're in the air or have the engine running, you never put it in the off position. As you can see, there's a little safety to prevent that from happening. We never want to run a tank completely dry, especially if the aircraft is equipped with electric fuel boost pumps, as this Piper is. When we run a tank dry, of course, the engine's going to stop. It'll keep freewheeling, but you can get a vapor lock, which can make it impossible or very difficult to restart, something we never want to happen. Below the flight instruments, we have the engine instruments. And starting on the left in this Piper, we have oil pressure, oil temperature, alternator amps, and our fuel gauges. I'll turn on the master switch, which is what we need to do to see how much fuel is in the left and right tank. And as you can see, we have 25 gallons in the left tank and only 10 gallons in the right tank. I want to point out that you never, ever completely trust the fuel gauges in a light aircraft. The way we determine range is to know how much fuel we have and then to figure out how many gallons per hour we're going to burn. That'll tell us how much we can get out of each tank. The best way to do that is to visually inspect the tank or take off with a full tank. But I want to just comment, don't ever completely trust these fuel gauges or you might run out of gas. This is the power quadrant, and I have my hand on the throttle. The throttle works just like a car. We push it in to go and out to stop. Airplanes have two items you'll never see in a car. A primer switch, which puts fuel directly into the cylinders before starting, and the mixture control, which is this red lever. The mixture controls the fuel-to-air ratio. It's important for us to have control of this. As we go up in altitude, there is less air, or we might say the weight of the air is less. So if we want to have the right ratio of fuel to air, the mixture control lets us feed less fuel to the engine at higher altitudes, and we do this by leaning or pulling the mixture control out. During takeoff and climb, we use a richer mixture. By richer, I mean a little more fuel than is needed because this helps engine cooling. Once we get to cruise altitude, we usually lean it out for maximum performance and efficiency. This can be done with the exhaust gas temperature gauge, which is over to the right. You'll always want to remember to richen the mixture as you begin a descent. Otherwise, you might find that there's too much air for the amount of fuel and the engine dies when you add power to level off. If this were to happen, simply push the mixture control in some and power should come back. Sometimes it's necessary to take off from high elevation airports with the mixture partially leaned. Otherwise, the engine runs rough because you have too much fuel for the amount of air. Don't forget we are talking about the weight of fuel and weight of the air when we are talking about these ratios, which are normally 15 parts of air to 1 part of fuel, or we call it 15:1. Now we're looking at the aircraft engine. Its operation is similar to an automobile. It uses gasoline. It has 4 strokes to get 1 stroke of power. And one of the major differences is it's air-cooled. There are fins on the cylinders to dissipate heat that comes in from the front of the cowling and passes through the engine. Another major difference is this engine is horizontally opposed. The cylinders are horizontal to the Earth's horizon, and they're across from each other. Now we're looking inside of one of the engine's cylinders. This is where combustion takes place. There is an exhaust valve, intake valve, and 2 spark plugs. As the fuel-air mixture explodes, the piston is forced down. Lots of pressure is applied to the connecting rod, which in turn rotates the crankshaft, which then turns the propeller. Really, there are 4 strokes that make all this happen. That's why aircraft engines are called 4-cycle. The first cycle is intake. The fuel air is sucked into the cylinder, and you'll notice the intake valve is open. The second is compression. The valves close, and the piston moves up. The third is power. The fuel-air mixture is ignited by the spark plugs. This creates the power to turn the crankshaft, which turns the propeller. And the fourth is exhaust, the last step. Exhaust valve opens, and the burned gases exit the cylinder. This hot gas is used to make cabin heat and carburetor heat, which we'll talk about in just a moment. Aircraft engines, unlike car engines, have 2 spark plugs that are ignited from 2 separate magnetos, which operate on their own magnets. This gives us better combustion performance and an added measure of safety with these dual independent magneto systems. The magnetos are operated by the ignition key and are completely independent of the airplane's electrical system. This means the master switch can be turned off in the flight without killing the engine, something you might have to do someday if there's an electrical fire. As you can see, the ignition key has 4 positions: off, right, left, and both. Plus, you might say there's a 5th position, which is used for starting the engine. You always operate with both unless you discover a bad magneto in flight, in which case you could operate on left or right only, but you'd have less power available. By the way, there's a ground lead, often called a P lead, from the magnetos to the engine block. This causes the spark to stop when the key is placed in the off position. This is because the off position completes a circuit to ground. If this ground wire is broken, the off position will not stop the engine. Generally, we starve the engine of fuel with the mixture control to stop it anyways. Can you think of another way to stop the engine? Sure, just turn the fuel selector off, but it will take the engine a minute or 2 to die, and this is not a recommended procedure. Now we'll look at the induction systems, which mix outside air with fuel and deliver this to the cylinders. And there are 2 types. The first we'll talk about is fuel injection, and the second is a float-type carburetor. The least common in small training aircraft is fuel injection, though this is most common in high-performance aircraft, especially with turbocharged engines. Fuel injection works by injecting raw fuel directly into the cylinders during the intake stroke. And the advantages of fuel injection are a reduction in evaporative icing, since the fuel doesn't evaporate until it gets into the cylinder. There are no areas where it can create a cold area due to evaporation. A possible but unlikely spot for icing is the air intake on the cowling, but we have an alternate air control in the cockpit in case this were to get plugged up with ice. Second advantage is faster throttle response, better fuel distribution since fuel is metered directly into each cylinder, and this helps to give better fuel economy and more precise mixture control. The last advantage is better cold weather starting because the fuel is mixed directly with the air in the cylinder. But fuel injection has some big disadvantages too. They can be difficult or impossible to restart when the engine is hot. The fuel boils into vapor inside the lines that are next to the hot engine, and you get vapor lock. So if you make an intermediate stop, you may be shut down for an hour or so while things cool off. Fuel-injected engines can be difficult to restart in flight if you run a tank dry. Now let's look at carburetors. This is probably what you have in your training aircraft. Carburetors mix the fuel and air before it gets to the intake manifold, where it is distributed to the cylinders. The air first comes in the air intake up through the venturi, which is a narrow throat in the carburetor. A low pressure area is created which forces fuel to flow through the main fuel jet or discharge nozzle. Here it gets mixed with the air flowing through the carburetor. The throttle valve, operated by the throttle in the cockpit, regulates the amount of air and consequently the amount of fuel air going to the engine. So you really increase power by stepping on the air, not the gas. The fuel-air mixture then goes through the intake manifold and into the cylinders for combustion. As air flows past the venturi, which causes a restriction, its speed increases and its pressure drops. This causes the fuel and air mixture to expand in the carburetor, and the temperature then can drop between 40 and 60 degrees Fahrenheit. Both the expansion of air and evaporation of fuel causes this cooling. Now imagine this. The outside air temp is 70 degrees Fahrenheit, and it's a humid day. Well, what happens when the air is cooled by 40 or 60 degrees Fahrenheit? You're right, the moisture gets squeezed out and forms as ice around the throttle valve and in the carburetor throat. Since we can't look in there, how do we know if there is ice or if we're likely to get carburetor ice? Well, first let's consider which conditions are most likely to form carburetor ice. If the outside air temp is between 20 and 70 degrees Fahrenheit, plus if there's high relative humidity or visible moisture. Carb ice doesn't give a lot of warning. In an airplane with a fixed pitch propeller, you'll see a drop in RPM. That's if you're not continually adjusting the throttle. In a plane with a constant speed propeller, you'll get a drop in the pressure in the intake manifold because less air is getting through. RPM will stay the same because that's the purpose of a constant speed propeller, which we will talk about in just a moment. The only way to get rid of carburetor ice is to use full carburetor heat to melt the ice. And in real life, this happens very quickly. The textbook says this about carb heat. Use of full carb heat will cause a decrease in RPM, then a gradual increase in RPM, well, maybe sometimes. By the way, the heated air comes from a muff around the exhaust manifold. Applying carb heat will enrich in the fuel-air mixture because hot air weighs less than cold air, so we might say it's less dense. Carb heat decreases engine output. Less dense air always does, and increases the operating temperature of the engine, which is caused by the hot air. And the operating principle of float-type carburetors, which we've been discussing, is the difference in air pressure at the venturi throat and the air inlet. After learning all this bad news on carb ice, you might wonder if there are any advantages over fuel injection. And the answer is yes. Easier hot weather starts, and it's easier to start if you run a tank dry. Well, that wraps it up on carburetors. Now let's talk about oil. As you probably already know, all engines use oil. And this oil has very important functions in the engine. First, it lubricates hundreds of moving parts. Second, it removes heat from the internal areas of the engine. Oil coolers are found on large reciprocating engines just for this purpose. If you're low on oil, your engine can overheat. And as I'm sure you know, this can cause loss of power, excessive oil consumption, and permanent internal damage to the engine. Detonation and pre-ignition can also damage your engine. Normal combustion occurs when the fuel-air mixture ignites and burns after the piston has passed top dead center at the end of the compression stroke. Pre-ignition is just that, ignition prior to the normal ignition, or ignition before electrical arcing of the spark plugs. Hot spots cause the mixture to burn at the wrong time. This uncontrolled firing can damage the engine and cause excessively high cylinder temperatures. You can usually prevent this by cooling the engine. A richer mixture, lower power setting, or higher airspeed will help to do this. Detonation occurs when the fuel-air mixture explodes instead of burning evenly. This develops stresses that can destroy the engine. Detonation can be caused by too low a fuel grade, high engine temperatures, or too lean a mixture, which causes high engine temperature. Detonation may cause a pinging or knocking sound. It's most common when you're climbing with full power. So if this ever happens, lower the nose, which gives you more airspeed, reduce power, and enrich in the mixture. You want the engine to run cooler, and this will often do the trick. There's one more thing we can do to hurt our engine. That is rapidly opening and closing the throttle, which can detune the engine's crankshaft counterweights. Now let's review the two types of propeller systems. The first, which we are most familiar with, is a fixed pitch propeller, and it's just that, fixed pitch. The angle cannot be changed. It is set by the manufacturer at an angle to give fair performance at both low speeds during takeoff and high speeds during cruise. But it only gives you fair performance, because we want to take a small bite of air during the takeoff roll and a big bite of air during cruise. But if the pitch is fixed, it can't do both very effectively. There is an answer, and that's a constant speed propeller, which is a controllable propeller. It's called a constant speed propeller because there's a propeller governor which automatically changes the prop pitch or blade angle to counteract any tendency of the engine RPM to vary from the setting you select. You use a low blade angle or decreased pitch for takeoff. This allows the engine to develop its maximum RPM or power on takeoff, which is what we always want to do. In other words, we take a small bite of air. And we use a high blade angle or increased pitch for our best performance at cruise speed. A real advantage to constant speed propellers is that we can get anything we want between takeoff and cruise. Now let's take a look at how this works in the cockpit. There's one additional instrument that you won't find with a fixed pitch prop setup, and that's a manifold pressure gauge. The manifold pressure gauge tells you how much air is in the intake manifold of the induction system. At sea level, this gauge reads 29 inches of mercury. That's because sea level pressure is 29 inches. This pressure decreases 1 inch for every 1,000 feet we climb. So here in Denver, the mile-high city, the gauge reads only 24 inches of mercury. The manifold pressure gauge shows us if we are making the engine work too hard at a given RPM or propeller setting. With a constant speed prop, engine RPM is controlled with the propeller control and power by the throttle, which is measured on the manifold pressure gauge. Now let's take a look at how some of this would look from the cockpit and how we'd handle a constant speed propeller. On takeoff, we'd have our propeller control full in to give us decreased pitch or a small bite of air so we can get maximum performance from our engine. The mixture control is in the rich or near rich position, and the throttle is off. As we increase power on takeoff, we want to make sure that manifold pressure, which is controlled by the throttle, doesn't increase past our RPM reading. Let's just suppose here in Denver, well, we don't have to suppose, the most manifold pressure we're going to get in a normally aspirated engine or an engine without turbocharging is 24 inches. And as we can see at takeoff in Denver, we have about 2,450 RPMs, and that's acceptable. Now, as we climb out, one thing we don't want to do is we never want to overstress the engine by having manifold pressure increase RPM. So we would not take this propeller control and pull it out if it would cause RPMs to go below our manifold pressure reading. Let's go back to our takeoff situation, or takeoff power. During level off, the order in which we would adjust things would be we would pull throttle back first to reduce manifold pressure. Then we'd bring our RPM back or increase the blade pitch to take a little bigger bite of air. By doing things in this order, we prevent manifold pressure from exceeding RPM. Let's say we want to go back into a climb from cruise. First, we'd increase the propeller control. We'd push it in, or we would decrease pitch so we can get more performance. Then we'd push in the throttle. This prevents manifold pressure from exceeding RPM, a condition that we don't want to see because it tends to overstrain the engine. There are a few more little things we need to talk about before we wrap it up on aircraft engines. Generators and alternators charge the battery and give us the direct current needed to operate the electrical system. Alternators are preferred since they are smaller, lighter, and provide a constant output at just about any RPM. This means they're good charging at low engine RPM, which is not possible with the old generators. You might someday hear the term inverter. This is a unit that changes direct current to alternating current. And as you probably know, alternating current is what we get from the wall outlets in our homes and offices. And direct current is used for cars and airplanes. Turbochargers allow sea level pressure to be maintained to very high altitudes. A turbine wheel is spun by exhaust gases in the exhaust manifold. This compresses the outside air and packs it into the intake manifold. Basically, a turbocharging system gives you sea level performance up to the service ceiling of the airplane. It's great for high altitude operations, but you'll need to keep an eye out for high engine temperatures that can lead to pre-ignition and detonation. There's one more item you need to know about, and that's hand propping. You don't want to ruin your day if you come out to the airport and find that the battery's dead. Normally the battery starts the engine through a starter, and of course the switch we've seen in the cockpit, but you can also hand prop it since the magnetos are independent of the battery's electrical system. But we want to make sure we do this safely. You want to make sure you have a competent pilot at the controls, that the tail is tied down, and that you have wheel chocks on the main gear. The FAA says that this is done from in front of the plane, the propping, by putting your hands on the prop and pulling down. If you use this method, you want to make sure you don't wrap your hands around the propeller, but hold your hands flat on the blade and pull down. A technique I used a lot as a pilot in Alaska flying in the bush when I didn't have a competent pilot at the controls and I didn't have the wheel chocks in or the tail tied down was to get behind the propeller. I would set all the controls the way I wanted them. I would put wheel chocks on. I would attempt to tie the tail down, but I would come and pull the propeller down. And the reason I'm doing this from behind is as the engine starts, if the airplane takes off, it gives me the ability to get up on the wing or grab a strut if it's a high-wing plane, jump inside and make whatever changes I need to the controls. Safety is the key here. That'll wrap it up for our engine operations section. Now you've learned what it takes to keep your engine running happily and smoothly.
Now we'll get into our engine operation questions, starting on page 3 with question number 30. In comparison to fuel injection systems, float-type carburetor systems are generally considered to be...
Number 3, more susceptible to icing than a fuel injection unit. Fuel injection units really can't get carburetor ice because you don't have a carburetor. The only place that can possibly ice is at the air intake up in front of the cowling. And if that were to happen, we have an alternate air control in the cockpit to bypass that. So if there is any icing in a fuel injection system, which is rare, we do have a way to take care of it.
Question 31. The operating principle of float-type carburetors is based on the...
Number 2, the difference in air pressure at the venturi throat and the air inlet.
Question 32. The presence of carburetor ice in an aircraft equipped with a fixed pitch prop can be verified by applying carburetor heat and noting...
Well, this is the FAA's classic answer, even though I don't agree with it, and it's answer 4, a decrease in RPM and then a gradual increase in RPM. I was a pilot in Alaska when I was younger, and I was flying from Anchorage to Fairbanks in my Cessna 150 that I used for training, and I was over the Alaska range, over some wild country, and all of a sudden I adjusted my mixture control and noticed that I was getting like a 200 RPM variation. I thought, wow, isn't this something? That I could hardly ever see anything on the TAC when I adjusted the mixture. Now I'm getting this great variation. Well, I got suspicious, and I pulled on the carburetor heat, and the engine just plain stopped. Well, it did, because it ingested so much water. So I immediately shoved the carburetor heat back in, and the engine started. I mean, a few thousand feet below me, I've got terrain where I couldn't make a forced landing. So what I did is I would put the carburetor heat on a little, it would melt some ice, the engine would choke, and I'd put it back on, off and on, until I melted all the ice. Then I left just enough carburetor heat on to prevent more ice from forming. None of this is what the FAA wants you to know. None of this is explained in an airplane flight manual. My whole point is you're going to have to experiment when you get carburetor ice to see what'll get rid of it and what'll keep it away, regardless of what the FAA says in their answers. So the answer's for that the classic example is that you get a decrease in RPM and then a gradual increase in RPM. But if you have a lot of ice, you're going to kill the engine when you turn the heat on.
Question number 33. Applying carburetor heat will...
enrichen the fuel-air mixture, and that's because hot air is less dense. The molecules, what creates the heat is the molecules hitting each other, moving further apart. We don't have as dense of air, and we have the same amount of fuel. So if you have the same weight of fuel and less weight of air, you're going to have a richer mixture.
Question 34. What change occurs in the fuel-air mixture when carburetor heat is applied?
Well, the same answer. Number 4, the fuel-air mixture becomes richer.
Question 35. If an aircraft equipped with a fixed pitch prop and a float-type carburetor, the first indication of carburetor ice would most likely be...
Well, technically, most likely, it would be a drop in RPM. But here's a problem that an inexperienced pilot's going to have. You're chucking along, you know, you're happy as can be, you know, working out your little navigation problems, thinking about what you're going to do when you get where you're going, showing off your wings. If you see a little decrease in RPM with the types of trainers you fly, you're going to figure that the linkage is a little loose and the throttle's working its way out, and you're just going to keep pushing it back in. You probably won't be aware of the fact that you have carburetor ice. So one of the things we want to say here is you don't want to continually be adjusting the throttle when you fly, or you'll never be able to see ice. The answer is number 4. You'll see a loss of RPMs, according to the FAA.
Question 36. The use of carburetor heat tends to...
Number 1, decrease engine output and increase operating temperature, and the only reason is because you're dumping hot air in the engine, so the engine's going to get hotter, and it's not going to work as well because you're putting less dense air in there, and you don't have quite as much of a bang in the compression area of the piston or where the cylinder is with the hot air.
Question 37. One purpose of the dual ignition system on an aircraft engine is to provide for...
Number 1, improved engine performance. Also, an answer isn't here is it's improved safety. In case one magneto were to blow or one half of your ignition system were to fail, you wouldn't have a complete engine failure. You'd be able to operate on one other set of mags, and you'd have probably about 100 less RPMs because it isn't quite as efficient. But the purpose of the dual mags is to give you better engine performance.
Question 38. An abnormally high engine oil temperature indication may be caused by...
Well, number 1, the oil level being too low.
Next page, question number 39. Excessively high engine temperatures, either in the air or on the ground, will.
Number 2, cause loss of power, excessive oil consumption, and possible permanent internal engine damage.
Question 40. For internal cooling, reciprocating aircraft engines are especially dependent upon.
Well, the only way they cool internally is by the circulation of oil. The oil picks up the heat, and it either cools down when it's sitting in the sump or in the bottom of the engine, or in most airplanes beyond the level of our very basic trainers, they have oil coolers mounted up in the cowling. As the oil passes through there, it's just like a radiator, it cools the oil off. It's real important for us to know that oil is just as important for cooling the engine as lubricating the engine.
Right. Question 41. If the engine oil temperature and cylinder head temperature gauges have exceeded their normal operating range, the pilot may have been.
Well, number 4, operating with too much power and with the mixture set too lean.
Question 42. Filling the fuel tanks after the last flight of the day is considered a good operating procedure because this will.
Well, number 3, prevent moisture condensation by eliminating airspace in the tanks.
Question 43. Detonation occurs in a reciprocating aircraft engine when.
Number 4, the unburned charge in the cylinders explodes instead of burning normally.
Question 44. If a pilot suspects that the engine with a fixed pitch prop is detonating during climb out after takeoff, normally the corrective action would be to.
Now, this is something that will happen to you in real life, and what you want to do is just pull some power back, reduce some of the internal pressures on the engine, which is causing the detonation, and number 2, retard the throttle.
Question 45. If the grade of fuel used in the aircraft engine is lower than specified for the engine, it will most likely cause.
Number 4, detonation. Again, if you found that you did have fuel that wasn't doing the trick, whether intentional or unintentional, you might try operating with a little less power, and it might save the engine, allow you to get where you're going.
46. The uncontrolled firing of the fuel-air charge in advance of normal spark ignition is known as.
Well, I've got a little way to help you remember this, the answer to this, because detonation and pre-ignition are interchangeable almost with what you see in the cockpit as far as a pinging sound. The word advance in the question we could use to the word pre in the answer, so the answer is number 2, pre-ignition. So if you see that word advance, just think of advance or pre, so pre-ignition.
I'm just saying that it starts its combustion before the spark plug is actually firing, so it's pre before the ignition. Right. Question 47. On aircraft equipped with fuel pumps, the practice of running a fuel tank dry before switching tanks is considered unwise because.
Number 1, the engine-driven fuel pump or electric fuel boost pump may draw air into the fuel system and cause vapor lock. This is very, very true and can happen to you.
Question 48. Which would most likely cause the cylinder head temperature and engine oil temperature gauges to exceed their normal operating ranges?
Well, before we heard that it can happen by having low oil quantity, it can also happen by using lower than specified fuel. So the answer is number 1, using fuel that has a lower than specified fuel rating.
Cheaper. In other words, don't use cheaper fuel. Always, if you have to go with something other than the recommended fuel, go more expensive.
Just like we mentioned in the curriculum, you can always jump higher with fuel grades in aviation. And there aren't that many choices because there's only 3 types of fuel. Then there's the stuff that Jeff uses, kerosene. But that's correct. You never go to a lower fuel grade.
Question 49. What type fuel can be substituted for an aircraft if the recommended octane is not available?
Well,
we just talked about
we just explained it. Number 1, the next higher octane aviation gas can be used.
Question 50. When cruising at 9,500 feet MSL, or mean sea level, the fuel-air mixture is properly adjusted. If a descent to 4,500 feet MSL is made without readjusting the mixture control.
Well, let's think about what's going to happen here. You're up at 9,500 feet, and we know that the air at 9,500 feet is thinner or has less weight than the air at 4,500 feet. Remember, we're in an ocean of air. That the air is voluminous. There's a lot there. What's funny to us human beings is we can't see it because it's a gas. But if we were in a vacuum where the conditions were stable and we took a parcel of air and a parcel of water and they were both equal, the air would weigh twice as much as the water. Well, how do we apply that to this question? What the question is saying is if we're up here and we come down here without adjusting the mixture, what's going to happen? Well, you've got, what happens as we get down here? You have heavier air.
More air, but the fuel's the same, right?
Yeah, so what we're doing to our fuel-air ratio then is adding more air and less fuel, which gives us a leaner mixture. This is the way you're going to have to figure these problems out. You're going to have to mentally think about what's going on. So let's read the question. While cruising at 9,500 feet, the fuel-air mixture is properly adjusted. You descend to 4,500 feet without touching anything. What's going to happen? Your mixture is going to be too lean. This is a problem that happens anytime you forget to richen the mixture as you descend. Answer is number 1. The fuel-air mixture may become excessively lean. It might become so lean that as you, let's say, get down to 4,500 or 3,000 feet to level off or to get to an airport, you throw in the power, the engine's just going to die. If that ever happens, don't get panicky. Just go ahead and enrichen the mixture a little bit. Another problem that can happen in descending is that you can get carburetor ice. Even though it's not asked in the questions here, you don't ever want to leave that throttle closed for a long time in a descent, or that's the most conducive situation to getting carb ice if you've got some visible moisture.
Question 51, next page. During the run-up at a high-elevation airport, a pilot notes a slight engine roughness that is not affected by the magneto check but grows worse during the carburetor heat check. Under these circumstances, which of the following would be the most logical initial action?
Well, number 1, we want to check the results obtained with a leaner setting of the mixture control.
52, the basic purpose of adjusting the fuel-air mixture control at altitude is to?
Well, number 2, to decrease the fuel flow in order to compensate for decreased air density.
Let's go to page 9 and question 108. Question 108 on page 9. Which condition is most favorable to the development of carburetor icing?
Well, this is like a classic question and answer that's been on the FAA exams as long as I've been in this business, which has been all my working life. And it's number 4, temperature between 20 degrees Fahrenheit and 70 degrees Fahrenheit and high humidity. You remember in the curriculum we discussed that the air can cool up to 40 to 60 degrees through
the
Venturi effect and the expansion of the air as it comes past that point in the carburetor. So it means even at 70 degrees, it cools it down by 60 degrees, you're right in the freezing area.
Question 109, the possibility of carburetor icing should always be considered when operating in conditions where the...
Number 4, the temperature is as high as 70 degrees Fahrenheit and the relative humidity is high.
Lots of moisture. Next we'll go to page 34, question 416. Page 34, 416. How is engine operation controlled on an engine equipped with a constant speed prop?
Well, number 1, the throttle control's power output is registered on the manifold pressure gauge, and the propeller control regulates engine RPM.
417. What is an advantage of a constant speed propeller?
Number 4, it permits the pilot to select the blade angle for the most efficient performance, and that's the whole purpose of a constant speed propeller.
Next page, question 418. A precaution for the operation of an engine equipped with a constant speed prop is to?
You remember we talked about how you can overstress or develop too much pressure in the engine, and the analogy we made was stepping on a car in 4th gear. So the answer is number 4, avoid high manifold pressure settings with low RPM. Just think of an automobile. If you're in 4th gear and you're only going 20 miles an hour, you've got low RPMs, the engine isn't turning fast, you're all of a sudden throwing a lot of pressure inside of the cylinders by stepping on the gas. You let a lot of air in and a lot of fuel-air mixture to explode. So that's a situation we never want to get into. You can overstress your engine, you can actually blow it up. Answer 4.
Question 419. When starting an airplane engine by hand propping, it is extremely important that a competent pilot...
Number 2, be at the controls in the cockpit. I want to point out that number 3 looks good but isn't. It says a competent pilot, number 3, in the cockpit in charge and call out the commands. The difference here is if you're hand propping it, you call out the commands, not the guy in the cockpit.
420. The first action after starting an aircraft engine should be to?
Number 1, adjust for proper RPM and check for desired indications on the engine gauges.
421. What action can a pilot take to aid in cooling an engine that is overheating during a climb?
Well, the only option they've given you here is reduce rate of climb and increase airspeed. If you have call flaps on your plane, which you'll have on more high-performance single-engine planes you'll be flying once you get your license, a lot of times opening the call flaps will bring that additional air in for cooling, but that's not an option here, so number 3 will do.
Question 422. What is one procedure to aid in cooling an engine that is overheating?
Number 1, we enrich in the fuel mixture.
And question 423, the last engine question. The most important rule, remember, in the event of a power failure after becoming airborne is to?
Well, the right answer here is number 4, maintain safe airspeed. But let's look at the alternative answers. Number 1, quickly check fuel supply for possible fuel exhaustion. Well, let me tell you, I got a little more experience than you, and so does Jeff. And if my engine failed right after takeoff, I wouldn't be checking for fuel exhaustion, but I'd sure at least make sure I was on a proper fuel tank, because you can bring that power back pretty quick with starved fuel in a lot of airplanes, but that's not what they're looking for. Number 2, determine the wind direction to plan for the forced landing. That's exactly what I would do. If I had an engine failure 200 or 300 feet above the ground, I'd be thinking, where's the wind? I'd be lowering my nose, looking for a place to land.
Wow, why would you be lowering your nose?
Well, that's what we're going to get to. That's what we're
answer
don't take
number 4.
away my question.
Okay.
Number 3, turn back immediately to the takeoff runway. Well, if you had 400 or 500 feet and you didn't have a real strong headwind, that might be an option, but it would be something that only an extremely experienced pilot could do, because he would know at what point he could stall or at what point he might not make the runway and then say, well, I'm not going to make this runway, I'm going to go there, or I'm going to go there. But that's not within the realm of your ability. So number 4 is what the FAA wants you to do and what us instructors want you to do. If you ever have an engine failure right after takeoff, your first concern is to maintain safe airspeed, then find out where the wind is or think about that, look for a place to land, and try to restart the engine. So number 4 is the correct answer, but the way we do it in real life is we do number 4, we do number 1, we do number 2, and only if we were high enough would we consider number 3.
And that completes our discussion about engine questions. You know, it's interesting talking about all the reciprocating engine questions, and this is just a small sampling of different problems that can go wrong. In my experience, I fly jet engines, and they're much more technically advanced than a reciprocating engine, but from the operator's standpoint, they're very simple to operate. You just spin it up, well, you throw some air to it to get the engine rotating, throw in some gas, and when you're through with it, you shut off the gas and the thing quits. And you have engine heat, de-icing like you have carburetor heat and that sort of thing. But it's a very simple piece of machinery to operate, not so simple to build, though. So we've really discussed everything that the FAA asks about engine questions on the private exam.
Now you should know how to keep it running happily and smoothly.
Before we start with the weight and balance questions, we need to mention just a few terms to lay a good foundation. These terms we'll be using in answering all of these questions. The first term I want to mention is CG, for center of gravity. The center of gravity is a point about which the airplane would balance. In other words, half of the weight would be in front of the CG and half of the weight would be in back of the CG. In other words, you could consider balancing this airplane on the head of a pin at the location of the CG. Now the CG, or center of gravity, has limits. You have allowable forward and aft CG. If the CG gets in front of or forward of the forward limit or aft of the aft limit, the airplane may not be controllable and certainly is not stable. So that's why you have allowable CG limits. In considering the gross weight of the airplane, the gross weight or total weight of the airplane is equal to the empty weight, any payload, and this, if you're a commercial operator, it would be what pays your way. In other words, it would be passengers, baggage, and freight, and then fuel. So gross weight, payload and fuel equals, or excuse me, empty weight, payload and fuel equals the gross weight. And then the last item we need to mention is the weight of fuel and the weight of oil. Gasoline is 6 pounds per gallon, and oil is considered to weigh 7.5 pounds per gallon. And if you forget those numbers, I'll show you as we go through some charts where you can actually pick those numbers up again. So with that basic background, why don't we go into the questions, starting on page 30, question 373.
Okay, 373. Which of the following items are included in the empty weight of an aircraft?
It's answer number 4, unusable fuel and optional equipment.
Question 375. If an aircraft is loaded 90 pounds over maximum certificated gross weight and fuel, or gasoline, is drained to bring the aircraft weight within limits, how much fuel should be drained?
Now here we have to remember that the fuel weighs, or gasoline weighs, 6 pounds per gallon. So we're given that we're 90 pounds overweight. So how many gallons? You just divide 90 by 6 pounds per gallon, to come up with a number of gallons, and that's 15 gallons you would have to drain to bring the airplane within the allowable gross weight. I mentioned that the CG has limits. Well, obviously the weight has limits also. You can be too heavy for takeoff. So to bring it down within the allowable gross weight, you drain 15 gallons. That's answer number 4.
Okay, let's work our first real weight and balance problem. Question number 376. Jeff, I'm just going to let you explain the problem and the criteria here.
First of all, we use the formula weight times the arm equals the moment in most weight and balance problems. So weight times the arm equals a moment. The weight, of course, is the weight of the item, whether it's fuel or a passenger or a bag. The arm is the distance that that item is from the datum. The datum is an arbitrary chosen point on the airplane. Most airplanes, it's the nose of the airplane. However, it can be the firewall. In other words, the engine would be in front of the datum line and everything else would be behind the datum line. Or it could be, the datum line could even be chosen out in space in front of the airplane. But the manufacturer chooses the location of the datum line. The manufacturer will also tell you a certain seat, let's say the second row of seats, that would give you the arm. In other words, it's 86 inches aft of the datum. A certain baggage compartment or location of baggage storage would be so many inches away from the datum. And so all of these figures, those are the arms. In other words, it'd be inches. And then the moment is just the weight times the arm, and that's the mathematical result, if you will, of the multiplication. Weights in pounds, arms in inches, so moment is in inch pounds. So knowing that formula, we'll get into this first question, 376, using that formula. Weight times the arm equals a moment. We're given that the airplane empty weight is 1,495. We're given that the arm in inches is 101.4, and we're also given that the moment, which would just be multiplying the weight of 1495 times the 101.4, is 151,593. We're also given that the pilot and passengers weigh 380 pounds. We're given that the arm is 64 inches, or location of that row of seats aft of the datum line. So we would multiply 380 times 64 to come up with the moment, and that is 24,320 inch-pounds. Now we're given that we have 30 gallons of fuel and that the arm for 30 gallons is 96 inches. So 30 gallons times 6 pounds per gallon is 180 pounds. We need to do that math, and then we need to add multiply 180 times 96 to come up with a moment of 17,280 inch-pounds. So we add up all of the weights, and that's 2,055 pounds. We add up all of the moments, and that's 193,193 inch-pounds. Now they're asking for where is the CG, or how far aft of datum is the CG located. So we found the total of the weights and the total of the moments. We need to do one more piece of computation, and that's solving for the arm. The arm of the entire airplane, when we have the entire moments and the entire weight, would equal the CG. So the arm, which is the CG, would equal all the total moments divided by the total weights. 193 divided by 2055 for total weights is equal to 94.01 inches. And that would be the location of the CG aft of datum, and that's answer number 2, 94.01.
Jeff, why don't you explain datum just a little more, since it's an arbitrary term. Why don't you go into that just a little bit about what a datum line is and where it might be located and why?
Well, as I mentioned, the datum is chosen. It's arbitrary in that it can be chosen to be anywhere when the manufacturer builds his airplane and then comes up with the charts, weight and balance charts. Most aircraft choose the very nose, the leading edge of the spinner in a single-engine propeller airplane, multi-engine jet. It's the very tip of the nose is the datum. And then if you do that, if it's the very tip of the nose, then all distances are positive. In other words, all the weight, the whole airplane is aft of datum. So you can just say, everything starts right there at the datum and you have positive distances. Some manufacturers choose the firewall as this arbitrary location of your 0 point of figuring all of your datum lines or distances from datum. When you do that, everything aft of datum, the distances are all positive. Everything in front of datum, though, is negative. So you're going to be adding some numbers and subtracting some numbers, and that's why that's not the norm. Normally, as I said, the choice is to determine or just to place the datum at the nose. So now that you have this datum line, we're just saying that's our reference line. That's all a datum line is.
It's a point to measure from.
That's right. And so all distances for all of the rest of the items in the airplane are measured from that reference line. It's called a datum line. And the fuel, let's say, is 96 inches aft of datum. The front seat passengers are 64 inches aft of datum, and so on. And it'll always be listed in your weight and balance charts. The location of the of the arm, or I should say the magnitude of the arm, how many inches aft of datum. That's really all that the datum line is.
Thanks. Question 377. What is the maximum amount of baggage that may be loaded aboard the airplane for the CG to remain within the loading envelope? We'll refer to figure 33.
Okay, figure 33 is really a two-part figure. We have weights, and we can get moments, and then we have a loading center, or an envelope for the center of gravity. The top part, figure 33, is the loading graph. You can see there are lines for the pilot and front seat passengers, fuel. Now notice it says fuel 6 pounds per gallon. So if you totally forgot that fuel weighed 6 pounds per gallon, you could refer to figure 33, which is, of course, comes with the test, and find the answer right there to help us with the other answers as I mentioned. Rear passengers have a different line because you have the arm is farther away, the seats are farther away from the datum line, and then baggage or a passenger in the child seat is another line. So we're going to use these lines, and we can find weight off to the left and the moment, and notice it says moment divided by 1,000. So they've just divided all of these moments, inch-pounds, by 1,000 to get smaller numbers. In other words, it wouldn't be 15, it would be 15,000. All right. We go down to the bottom part of this particular graph, and we find, once we find the center of gravity, or moments, loaded aircraft moment, and the loaded aircraft weight, we come in to an intersection of these two from the moments and the weights, and we can now find if the CG is located within the CG envelope, or aft of CG envelope, or forward of the allowable CG envelope. So that's actually how we're going to use this chart. Let's look at the problem, and we're given that the empty weight is 1350 and the moments are 51.5. Now again, I would take weight times the arm equals a moment and make 3 columns. Weight on the left and then the moments on the right. So we're given that and that is moments divided by 1,000 now, so be sure you're comparing apples to apples. So it's 1350 under the weight and then 51.5 under the moment. Now they give us that the pilot and front seat passengers are 250 pounds, and so we go to our chart, figure 33, pilot and front passengers line, and 250 pounds, we just find, here's 100 pounds, 200, 250 pounds. We read over until we intersect with the pilot and front seat passengers line, and then we read down to get the moment divided by 1,000. When we do that, we come down something less than 10. Now notice this is 5 for the moment divided by 1,000, and this is 10. So each one of these little marks is 1/2. So we reading down from the front seat passenger, something less than 9.5, right around 9.3. So that's what we'd put under the moment column then, 9.3 for the pilot and front passenger. We're given that the rear passenger is 400 pounds. So we look back at the graph again to get 400 pounds off to the left, reading across now to the rear passenger line, finding that intersection, and then reading down. It would be less than 30, around 29.2 is what I come up with using my straight pen. We're also given that we have 30 gallons of fuel. Now if you forget that fuel is 6 pounds per gallon, we'll use the chart to actually determine that. Notice on the chart you have dots. One dot with a 10, that's 10 gallons. One dot with a 20, 30 gallons. Here's 38 gallons with 1 star and 48 gallons with 2 stars. To find out what those stars mean, you look down here to the right. 1 star means standard tanks. In other words, they would tell you in the problem that you had standard tanks, so you would use 38 gallons. 2 stars is long-range tanks, and again, in the problem, they would tell you you have long-range tanks, so you would put in 48 gallons. Anyway, back to our problem, they give us that we have 30 gallons. You can either multiply 30 times 6 to get our weight of 180 pounds, or you can just look over to the left to get our weight, 180 pounds for 30 gallons, and you read down again to find the moment divided by 1,000 for the fuel, and that's 8.7. So we'd put 180 pounds under the weights column and 8.7 underneath the moments column. And then finally they give us that oil is 8 quarts. Now if you forget that oil is 7.5 pounds, 8 quarts, by the way, if you forget, is 2 gallons. But if you forget that oil weighs 7.5 pounds per gallon. You look down on the bottom of this chart and it'll tell you, bottom of the top portion of the chart, it says note number 2, engine oil 8 quarts equals 15 pounds or 7.5 pounds per gallon, and the moment is minus 0.2. In this case, the datum line is probably located at the firewall because the oil is in the engine. Notice you have a negative moment. You wouldn't have a negative moment unless the oil was located in front of the datum line. So we know that we're given that we have 8 quarts of oil, so that is 15 pounds given in note 2, and that a moment is minus 0.2. So you put 15 pounds underneath the weights column and minus 0.2 underneath the moments column. Now I've written all of those figures down, and we can see our total weights column here giving us, if you add all of the weights up, that's 2195 for a total weight. And the total moments, and that is moment divided by 1,000, add that up, and that's 98.5. Now they ask us, what is the maximum amount of baggage that may be loaded aboard the airplane? So we need to find out, first of all, what the maximum weight of the airplane is, and then we need to find out whether or not that moment is going to be within the moment's envelope. So we look back then at figure 33, and the bottom portion of figure 33 now, to get the first figure, the maximum weight. The maximum allowable weight of the airplane would be this upper line, and we'd read over to the left to get the total weights, and that's right at 2,300 pounds. Now in adding up all of our weights, we came up with 2195, so we just subtract 2195 from 2,300 pounds to get the amount of baggage that we can carry, and that's 105 pounds. Now you can say, okay, 105 pounds, that's the answer, and it is answer number 2, but you need to go one more step, and that's to find the weight for 105 pounds of baggage, and we again go back in the upper portion of this chart for the baggage line, read over from 105 pounds, down then to find the moments, and that's 10.1. So we would add 10.1 to our moments, that giving us 108.6, and our total weight would be right at 2,300 pounds. So we look in the bottom portion of the chart now and find the intersection of 2,300 pounds with 108.6, which is our total moments, and that's right on this upper right corner. That's located within the normal category envelope, so it's authorized to put 105 pounds, or it's okay from the weight and balance standpoint to put 105 pounds of baggage on board in these conditions. So answer number 2, 105 pounds, is the correct answer. Now, I should mention, that's a complicated, just following through this, probably you're wondering like, whoa, what did he say? All I did is a recap. We took our formula, weight times the arm equals a moment. We added up all the weights that's given for everything except for fuel. We had to multiply 6 times 30 gallons. And we added up all the weights. We added up all the moments that we found from that chart. And we came up with total weight without baggage and total moment without baggage. To find out how much baggage we can put on board, we need to find out the maximum weight of the airplane. So we went to the bottom chart to get 2,300 pounds as a maximum weight allowable on this airplane. We just subtracted what we had on board, 2195, from 2,300 to get our baggage weight, and then we made sure that after adding the moment of that baggage onto the total moment of the airplane, we were still within the loading envelope or CG range for the airplane, and we were. So that's in the quick and dirty a recap of how we did that problem.
By the way, this is for a Cessna 172. That's the charts we're looking at, even though it doesn't say so on the chart. And something you're learning is you just can't throw anything you want in an airplane just because there's a number of seats or fuel capacity or room in the baggage area to throw what you want. And a lot of times in real life, you'll be working this problem just like this to see how much baggage you can take and what's going to have to be left behind. Often, fuel is left behind because you might not need all the fuel you need to go somewhere. You don't fill your jet up every time you fly somewhere.
No, yeah, in fact, it costs money to carry fuel that you don't need. And I don't know what the figure is. It's about 7%. So you would burn off about 7% of the fuel that you're carrying that's excess, so it's actually costing you money to carry excess fuel. I'm not saying cut fuel down to the bare bones, because always have a nice little pad for whatever your particular conditions are, what the weather is, the runway conditions or whatever, but you don't want to take an excessive amount of extra fuel.
Yeah, and part of my point is in the training aircraft you've taken your lessons in, they get topped off after every lesson, so either the last guy pays the fuel bill or that's just the procedure, but there are instances on cross countries or short cross countries where you might not want all your fuel. And by the way, the same fuel truck that pumps it in can suck it out if you ever need it to get within weight and balance. And this is one area you never want to fudge, because if you were to get in an accident, the first thing they're going to do is add up everything in the airplane and see if you're over limits, and if you are, you're violating the regulations, and they'll put the blame on you.
And there's your violation and your license.
Question 378, top of page 31. Calculate the loaded aircraft moment per 1,000 of the airplane loaded as follows and determine which category when plotted on the CG moment envelope.
Well, we're going to refer to figure 33, which is the same figure that we talked about, and this time it's probably a little bit easier problem, though. They give us that the empty weight, again, is 1350, so you'd make 3 columns, weight, arm, and moment. 1350 would go under the weight, and the moment is given as 51.5, so you'd put that under the moment. Then they give us that the pilot and front passenger is 310 pounds, off to the left, 310 pounds, over to the pilot and front passenger, and down, you read 11.5 for the moment. So you'd put 310 under the weight column and 11.5 under the moment. That is, again, moment divided by 1,000. Then they give us that we have rear passengers of 96 pounds. 96, each one of these little lines is 10 pounds, so you're going to have to be in between lines. Over to the rear passengers line, and then reading down, looks like right at 7 for the moment divided by 1,000. Then they give us that the fuel is 38 gallons. Now again, 38 gallons has a little dot. You can read over to the left or multiply 38 times 6 to get the weight, which is what you want to put under the weight column. That's 228 pounds. Then you read down from that intersection to get the moment, and that is 11.0. And they give us, again, that the oil is 8 quarts. So we look down at the bottom just below this chart, and if you forget, 8 quarts is 15 pounds of weight for the oil, and the moment is minus 0.2. So I've drawn everything on, again, total weights and total moments. Total weights, 1350, 310, 96, 228, which is the fuel, and 15, which is the oil. Adding all of that up is 1999. Total moments, 51.5, 11.5, 70, 11 for the fuel, and a minus 0.2 for the oil. And when you add all of these and then subtract 0.2, you get 80.8. So we go back to figure 33 to get the look at the bottom part of this chart, to look at the envelope to see which category. We're either going to be utility category or normal category, and we found the total weights were 1999, or right under 2,000 pounds, and you read over until you intersect with 80.8. And when you do that, you are right on, again, the limit here of this inner utility category. So the answer would be 80.8, and you are a utility category aircraft for this particular flight, and that's answer number 2.
The reason you'd want to work this problem sometimes just for going out for flight training is you need to be in utility category to do certain maneuvers like spins and maneuvers, the commercial maneuvers like the chandelles and lazy eights that can cause some stress on the structure. You're limited by weight and balance for some flight maneuvers, which is why we have a normal and utility category. Let's move on to question number 382 at the top of page 31. Determine if the airplane weight and balance is within limits. We're going to refer to figures 34 and 35.
Let's look at figure 34 and 35, and they're large figures, but they give us the same information that we got from figure 33, but this is now in a column or tabular form. Looking at figure 34, we have weights for occupants, and we have a front seat with an arm of 85 inches, rear seat with an arm of 121 inches. We have fuel, and they give us a number of gallons, the weight for that number of gallons, and the moment. And again, all of these moments this time are divided by 100. They're not divided by 1,000, but 100. We have baggage or a fifth seat occupant column here, weight on one side, moment divided by 100. We have auxiliary wing tanks. We have oil. Notice it says oil is included in basic empty weight, so you're probably not going to use anything from figure 34 on the oil. Then right here we have 2 large figures. The empty weight is 2,015 pounds, and the moment divided by 100 for the empty weight airplane is 1,554. So we're going to use all of these figures under all of these numbers, I should say, from figure 34, just like we did before for our weight column and our moment column, and then we're going to use figure 35 to figure out whether or not within the CG envelope. So let's start with figure 34 and the conditions that we're given. We're given that we have front seat occupants of 340 pounds. Front seat occupants and 340 pounds, notice that the most we have is 200 pounds under front seat occupants. So you can do it one of two ways. You can break it down. 340 would be 200 plus 140, and you get 2 moments and just add those two together. Or you could take 340 pounds and multiply it by the arm that's given for that row of seats, which is 85 inches.